In the final part of this lesson on drag force, we're going to more closely examine the velocity function. We'll look at the graphical representation of the function, and we'll talk about the time constants that are used to describe the exponential or natural log functions in physics and in engineering. So let's go back and revisit our velocity as a function of time equation. This is the solution to the differential equation that we just solved on our last page of notes down here at the bottom. So I'm referring to this equation. I've put the mg on b as v terminal, and notice I've replaced this m divided by b with its own constant, which we call the time constant, tau. So this is the Greek letter tau, like torque, but it's a time constant in this case. So T-A-U. And it has to have units of time. So I have it down here, and please make sure you get all of this in your notes. This will be important for any future problems like this you solve in physics or engineering. It has to have units of time, and let's think about why does it have to have units of time. Well, if we look at our expression for velocity, the bracketed term goes from 0 to 1. It can't have units because our units are all here in v terminal. So we know that mg divided by b has units of velocity, but m divided by b, right? That m divided by b that we get underneath the little t, and now we're setting it equal to tau, has to have units of time. So we now know the units for our proportionality constant in our f equals bv. It has to have units of kilograms over seconds divided by seconds, so the kilograms will cancel out with the kilograms in the mass. We're left with seconds. Now the function itself will have this logarithmic increase to a Vmax value as it shows here, and you have your graphing calculators for the AP test, so you certainly can graph it out. Now, to understand what a time constant is, you want to think of it as an actual time, and that's why I put in here this example time constant of 2 seconds. So let's say you were given the mass of the cat in kilograms. We were told the proportionality constant for the drag force B, and when we did that division, we got 2 seconds. Well, what's the meaning of tau being 2 seconds? Well, you get the meaning for the time constant, or tau, being 2 seconds when little t, the actual time, is at 2 seconds. So when the actual time is at 2 seconds, and we plug in 2 seconds for little t, 2 seconds for tau, we get 1 minus e to the minus 1, and we put that into our calculators, we get 0.63. So we are roughly 2/3. We're exactly 0.63, but roughly 2/3 to Vmax. So it's a very convenient parameter to use to compare exponential growth or logarithmic growth and exponential decays. So if we wanted to see how long do we have to wait to get this logarithmic increase to our Vmax, our terminal velocity, we can see that if we went out to 4 time constants, or in this case 8 seconds, so we get negative 8 divided by 2, or 4, so e to the minus 4, the bracketed term is 0.98. So here at 4 time constants, or after about 8 seconds in this case, we are 98% to our Vmax, so we're essentially at terminal velocity. We're going to crawl to terminal velocity from that point on. The last bit that we have to know for these types of problems is how to get the acceleration, and we know that because we know acceleration is the derivative of velocity. So we literally pick up our velocity equation. So we take, let me erase these additional comments I have here. So we are literally going to take our velocity equation and plug it in for the velocity and take the derivative, and you will see that we get an e to the u du. Derivative of e to the u is an e to the u du. So we do have to take the derivative of the negative t on tau, which gives us a negative 1 on tau. The two negatives here give us the positive out front. So tau is m on b, so we lose both the m and the b. We're just left with the g, and that should make sense that at time t equals 0, right, little t equals 0, the acceleration is just the gravitational acceleration because the drag force hasn't begun to increase based on F equals bv. And here you can see that we get an exponential decay for our acceleration function. So this sums up this entire drag force problem. It is a very mathematical-based analysis and solution. We've introduced new language with time constant, solutions to the differential equations. You have the videos you can rewatch as well. You have one example problem to do in the notes to do on your own. So at this point, you can pause the video. Try that example problem. When you unpause it, you can come back, and I'm going to go to the solution and show it to you in the video as well as going over it with you in class. I'm not going to explain it in the video, but just show you the solution. So pause the video and give it a try. Okay, if you're back, we can unpause, and let's look at the first page. So here it's a sideways drag force problem. You can pause the video here and take a look at this solution. Okay, if you're back, let's unpause. Here's our solution to the differential equation that we've just done. It's slightly different variables. So pause here again, look at your solution. Okay, and finally, the graphs. Pause here, look at these solutions and the point values, of course. So take a look at everything that is here in this note packet, and we, of course, can discuss and will discuss this in class.